Hello, and welcome to our video abstract for our paper Contemplating the Fate of Modified Gravity. In this paper, we explore the challenges and opportunities of modifying the theory of gravity and the philosophical and empirical dilemmas at the time of choosing the guiding principles for doing so. Gravity is described by the theory of general relativity, which was developed by Albert Einstein more than a century ago. General relativity is a beautiful and elegant theory, which has passed many experimental tests and explained many phenomena, such as the bending of light, the expansion of the universe, and the existence of black holes. However, general relativity is not perfect. There are some puzzles and tensions in cosmology, such as the nature of dark matter and dark energy, the origin of the cosmic inflation, and the discrepancy in the measurements of the Hubble constant. These problems suggest that there might be something missing out or wrong in our understanding of gravity, and that we might need to modify or extend general relativity. But how do we modify gravity? This is not an easy question to answer. There are many possible ways to change the equations or the assumptions of general relativity, but not all of them are physically meaningful or consistent. Moreover, there is no clear guiding principle to tell us which modification is the right one, or if there is a right one at all. One way of visualizing these modifications is to have a look at what components of the Einstein-Hilbert action are being altered. Here, for instance, we can propose a variable gravitational constant, we can alter the number of dimensions of spacetime, we can include models of unimodular gravity or mimetic gravity, which alter the square root of the metric. On the other hand, we can drop the assumption that is usually made in general relativity, that the connection is the Levi-Civita connection, and it depends on the metric. For instance, we can consider a connection that has torsion and non-metricity, and to work in a Poincaré or Einstein-Cartan framework, or we can put some conditions on this free linear connection, for instance, the condition of flatness, where then we are in the framework of teleparallel gravity. On the other hand, the Ricci scalar can be replaced by topological invariants, by the torsion scalar, or the non-metricity scalar. Moreover, it is possible to include nonlinear modifications, and then we are left to f of r gravity models, f of t, f of q, Palatini, etc. On the other hand, it is possible to propose scalar and vector fields in the matter sector, or there can be some mathematical equivalence between matter and modifications in the geometry. So, which one of these directions is the correct one to follow? We argue that we are mostly driven by the principle of simplicity, which means that we look for the simplest modification that can solve one or more problems. But what is the simplest thing to do is highly subjective, therefore not enough and even misleading. In our reflection, we stress to pay attention to study the landscape of possible modified gravity models, their classification and physical equivalences, and to study the foundational issues of all these models right from the beginning, in order to know which one of them can ever be viable. We invite you to read our paper for more details and discussions. Thank you for watching.